Okay, so we're going to look at vector databases. Last Wednesday, we had looked at embeddings, we had looked at chunking, and we had looked at document ingestion. So, of course, all of these fall under the general um, methodology for RAGs, which is a retrieval augmented generation. And I had explained all of that, what RAG means, the retrieval side of it, augmented side of it, and generation side of it. So now we are still in the retrieval phase, right? Retrieval phase is where you get the document, sorry, um, well, the ingestion phase is not part of the name. Retrieval is when you have done all of the ingestion, but this is ingestion phase. So ingestion phase is where you take document, you pull in the content of the document, you chunk it or you load it, you will decode it depending on the type of document. Then you will load it with document loader, you chunk it, you embed it, and then you will store it. So that's the first phase. There are two sides to the RAG. The first side is the ingestion side, and then the second side is the retrieval side. So the retrieval side is when you've gotten all the documents, you now want to use it as part of the context that your LLM will use to respond to the prompt or the query. So let's talk about vector databases. The vector database is essentially the last part of the ingestion side of the equation. The vector database allows you to store information using this semantic, you know, approach that we have talked about. So again, remember when you're talking about intelligence, we are referring to meanings, and that's why when we talk about embeddings, it's embeddings that give meaning, right? And we did a little bit of examples with embeddings last time, where we took a few words, right? And we were able to use the sentence transformer to get embeddings, basically the vector, the multi-dimensional array of what is actually a single vector of numbers. But that vector of numbers represents the meaning, and we could see what is in there, right? So when you take these embeddings, you have to store them somewhere. A regular relational database is not suited for this because you are storing numbers and large, quantities of numbers. Apart from just being able to store the numbers, you also want to be able to search numbers, um, the embeddings effectively. You want to search these embeddings. You want to find the ones that are similar, right? When you are doing search. In fact, vector databases are optimized for similarity search. Just think about, for example, if we are using a database like MySQL or Postgres or any other database, and you're using it for, um, um, geometric or, you know, the mapping kind of, you know, applications that we use those for, right? So for those, you would have to do some additional operations which a regular database cannot do. So you need to bring in those extensions or plugins, right, that will allow it to do it. So in the same way, vector database are specialized and optimized for storing embeddings, which are these vectors that we're talking about. And that's why it's called the vector database. Remember, the vector is just a list of numbers. It's also optimized for searching large amounts of vectors very fast. And the way it does this search is by similarity search. And there are three different approaches or methods, like we said, for similarity search. You have the cosine similarity search. You have the Euclidean distance, and then you have dot product. So these vector databases are optimized to be able to find vectors that are similar to each other. So think of it like if you were using it in the geomapping field, or if you were doing an application in geomapping field, you would have to get you have to be able to search for points that are close to each other in the same area. So in the same way, in fact, it's kind of the same algorithms that they use for that matter, because it's the same kind of thing. So you find that the traditional SQL or NoSQL databases that we are familiar with are not optimized for that kind of workload. You can't do the high dimensional vector operations on them. You cannot do the fast similarity search, right? And sometimes you can have millions to billions of vectors in a database. And that's where the vector databases shine very well. So the features of vector databases are one, indexing for similarity search. Um, Indexing for similarity search makes the database 100 times to 1,000 times faster when you want to run queries. It supports high dimensional vectors. So in the range of 384 to 4,096 dimensions, right? Last Wednesday when I did with the all mini, right? That model gives us 384. When we want to do a bit of hands-on, we'll see all of those, right? It also gives us metadata filters. So what this means is that in addition to searching similarity or searching by similarity using the vectors, you can add additional metadata that you can then search by those metadata. And it will be similar to what you would normally do in a regular database, or what we used to call context search, right? You know, based on text based searching. So you can actually put in filters. The essence of this is to help bring some kind of balance. Because if you are just doing similarity search using vectors, yes, you get semantic meaning, but there are other things you may want to do with metadata. For example, limiting it to which sections of material or which documents or which department, or even using it for access control as well. Because of course, all of these things are in one database, and if you do vector search, everything comes that goes in there will come out. But sometimes you may want to restrict based on access control, based on privacy. So there are many different ways. So it gives you the metadata filters, and it gives you the hybrid search, meaning that you can add keywords as well. So the keywords help to also search in the text, not just the meaning, but the words. They are very scalable. Like we said, some of them can hold lots of vectors, billions to billions. Of course, persistent, they can store your vectors safely, and you can retrieve them anytime that you store in them, so that when you have updates or you have new versions or the same documents, you can trigger, because essentially vector databases are more or less designed for RAG. So like I said, there are a bunch of enterprise level, SaaS cloud-based vector databases that give you a lot of the things that you would have done yourself in code, which we are going to do here. They still do it for you. For example, chunking, embedding, right? So it makes things easier. So, yeah, so that's the purpose of vector databases, storing embeddings to perform similarity search. That is really it. In a traditional database, if you wanted to do a search, you run an SQL query, right? Or SQL query, select blah, blah, where name is. So this is what you would do. And this would give you all the records that match exactly this word, right? So that's how traditional databases work. But with a vector database, what you are doing is you are searching in the embeddings, the vectors, right? And it is going to match anything that sounds like or has the same meaning as how do I reset my password, for example. It's going to give you everything that matches that. So we've already seen all of this. It gives you the vector storage, it gives you similarity search, metadata filtering, which is very, very useful for additional scoping of the information that goes in and comes out, indexing, of course, and then scalability. So there are a lot of, right now, there are a lot of different vector databases available. You have open source that you can download and run on your computer. So you have Chroma, you have Fice, you have Milvus, Hydrant. We'll try one of them. We'll try Chroma when we are doing our own hands-on. And then you have managed services, which are cloud-based vector databases. You just create an account, get an API key, and create create a store, right? An index, and you can then use it. So Pinecone, Weaviate, MongoDB, Elastic. So we'll also use Pinecone for a few of our hands-on so that you get a feel for both. One other interesting thing is that as of today, a bunch of traditional database management systems, the relational database management systems like PostgreSQL, MySQL, and co, now have extensions, right, or plugins that allow them to act as vector databases. So, for example, Postgres has PG Vector, which allows you, once you pull in that extension, you can then incorporate, um, embedding and all the capabilities of vector databases into a Postgres. So that's very helpful for if you people maybe you already have software that you have built, you already have an existing system that is built on those databases, and of course it will be difficult for you to migrate to some other stack. So you can then incorporate capabilities of RAG into that. Yeah, so some of the factors that you would consider would be things like scale, cost, latency, filtering capabilities, hybrid search support. These are some of the factors that you would consider when you are trying to choose or decide, um, you know, which of the vector databases that you want to use. Okay, so this we're going to try with the first two, like I said, Pinecone and ChromaDB. This is Cloud Vector. It's very fast. It scales automatically. It has metadata filtering, and it's designed for production grade RAGs. And this is how you can use them. You basically just import the Pinecone class, create a Pinecone instance. You pass in the API key, which you will get after creating an account. You can then create an index, or you connect to an existing index. And then you use offset. Offset allows you to add, um, you know, vector embeddings into that. So we'll see examples of that. Then ChromaDB is the same thing, right? But ChromaDB, you can have it running locally on your system, or you can use a hosted. So we are going to use a client that is local and it's easy to embed in your apps. It's great for prototyping, and it works with LangChain, Llama Index, and the rest. Fice is a Facebook AI similarity search. This is not really a database per se. It's more of a library that gives you the capabilities to do vector similarity search, right? So you store your vectors or you cache your vectors in there, right? And then you can do similarity search. But you have to give it a backend, essentially a database that it will operate on. So if you want to do a custom system, this is also good to use. All right. So by the time you pull all of these pieces together, that is eventually what will make up your RAG, is pulling together all these pieces. First step is chunk data. Well, before you chunk data, you have to first load the data. and then you chunk it, then you generate embeddings, then you store in the vector database, right? That is the ingestion phase of it. Then when the user wants to make queries and ask questions based on that data that has been loaded, this additional information that's been loaded, then you are now on the retrieval side of it. So the user is going to ask whatever the question is, you know, make a prompt. You now take this prompt and generate the embedding for it. So effectively, you are taking this prompt, you are finding the meaning, of this prompt. Then this embedding, you will use it to search for similar embeddings in the vector database. Embeddings are similar to the question. So that would basically find content in your database that the meaning relates to the question. And there'll be a lot of them. So you limit the retrieval to top K. K basically is a number. You could say top 5, top 10, top 3, right? When you retrieve those chunks now contain additional information that are relevant or related to the query or the question that was asked. And then you take the content of those documents, you add it to the prompt that you are sending to the large language model as part of the context for the prompt. And then you send that combined prompt to the large language model. So language model will now be able to answer and give you good answers because you've given additional information that wasn't in its training data set, right? It doesn't know about, but it needs to know so as to answer the question. So that's the beauty and power of RAG, right? It solves the problem of LLMs not knowing the private data, right? Now, what makes it more powerful is the fact that the embedding system, because you're using embeddings, it is semantic. You are pulling meaning. So you are effectively pulling data that matches the question that is closest to answering the question that is asked. And that's the power of it. So you can see where we are now using embeddings outside of the context of the large language models themselves. Okay, so we are going to try and pull all of this together. We will do a very simple naive RAG, and we are going to start off by using Python, and then after that, I will try doing the same thing again with JavaScript, so that we will see, um, you know, how both look like and how both work. Okay, so let's start off. So in this stack, I'm going to collab new. In this stack, I will first of all start by creating, I already have a Pinecone account, so I'm going to show you. So to get Pinecone, I have a collab. To get Pinecone, you can just search for Pinecone, right? And pinecone.io. So it's a vector database cloud solution. You create an account for yourself if you haven't already created one. And I would advise everyone go create an account so that you can use it to do a bit of practice. Um, yeah, so I already have an account, so I'm going to go in. To go in, of course, I clicked on start, right? Takes you to app.pinecone.io. I have to log in first. So yeah, I already have an account. Uh, let's see. I need to check where my account is currently. Okay, so well, pinecone is not very difficult. You can just put in your email. Let's go ahead and do that. And then when you put in your email, they will send a code to your email. Once they send the code to your email, then you can get the code and um, you put it in there. So let's see, I'm waiting for the code now. Okay, so I got the code. And yeah, as simple as that. So you log in. I think I already have, yeah, I'm building a small personal project. Uh, I want to do rags. Um, you can even look at the kind of data, whether you have raw files. Like I said, Pinecone has really evolved to the point where it actually does a full ingestion and chunking for you, right? But you can also do direct vector embeddings. Well, for me, it doesn't really matter. Yeah, you could also specify how you build AI assisted manual coding, no code, low code. Let me just choose manual coding, and then we could choose Python, JavaScript. These don't really affect a lot, except maybe the kind of tips and hints that it gives to you. Um, so you can create a new organization, or you already have a default organization created for you. Then what you do is you get an API key and create a, you go to the database, you can create an index. So I had already done a bit of stuff here before, um, for a lot of stuff. So you can go with the small rag. You can see it gives you, it allows you to configure. So I already have um, an index that I had created, but you can create a new index. I had also put in a lot of stuff here. So I'm going to start off with, let's start off with a new index. Let's see, I think I have exceeded my maximum startup plan for indexes. So what I will do is I will delete this index and create a new one. So um, so they give you five indexes. Um, okay, all right. So let's just learning, whatever you want to call it, all right? When you're creating an index, there are a bunch of things. In most of these cloud services, a lot of things are simplified for you. But I'm going to go through the raw pathway so that we can see. You can actually just choose a configuration here. And this configuration is to choose what model you're using for your embedding or as your embedding model. And they will have built-in models that can do the embedding for you. So in this case now I choose, you could choose Llama Text Embed, which is hosted on NVIDIA, or you could choose this multilingual large E5 large that is hosted on Microsoft hosted. Pinecone has its own, and so on. But I don't want to do any of that. I want to do a manual configuration. So I choose a manual configuration. When you're choosing a manual configuration, you have to decide a few things. But I think the three critical things that you have to decide are: one, what type of vector is it? Is it a dense vector or is it a sparse vector? Right? What is the dimension of the vector that comes out, the embedding vector? And what metric do you want to use for your similarity search? Do you want to use cosine, Euclidean distance, or dot product? Now, um, the answer to this question depend on your choice of embedding model. So let's go to Hugging Face, right? Where I want to use Hugging Face. So you go to Hugging Face, you're going to see a lot of different embedding models, and you can always figure out which one you would use. Go to the models page, and then you can choose sentence transformers. So for Hugging Face, the embeddings are all under sentence transformers, at least text embedding. Image embedding would probably fall elsewhere. So here, there's a lot of them, but I use this all mini. Now I'm going to click on this all mini LM L6 version 2, and you can get additional information. But some of the key things you look for is what is the embedding size? That is written here. This is a sentence transformers model. It maps sentences and paragraphs to a 384 dimensional dense vector space. So you have two of your answers from just this thing alone. The two answers you have, it's a 384 dimensional vector, and it's also a dense vector. So that answers two of your questions. So since we are going to use all mini, right, I then create an index. I know it's a dense vector type, and it's 384. Dimension is 384. Okay. The third one is your choice. So we'll go with cosine similarity, which like we said, that one calculates the the angular distance between the two vectors in a multidimensional space. I don't want to go into all of that physics stuff. Um, yeah, so that's it, right? Then the other things you can do advanced settings, but I'll just go with defaults. Okay, the cloud provider you can choose any of them, right? For now, since we are doing a free plan just for us to demo, yeah, we can go with AWS. So you can see that Pinecone is leveraging on existing cloud providers as a backend, the storage backend for whatever data and vectors and embeddings that you are going to um, upload. When you pick AWS, you have to pick the region as well. Then there is this deletion protection, which if you activate this, you will not be able to delete this um, until you remove this button. So that's to prevent you from accidentally deleting this index. Okay. So with all of this, I'm good to go. I'm just going to click on create index, and it will create the index. So index has been created. It's now initializing. It's in AWS US East 1. It's a dense embedding type. This is the host. So essentially a new AWS storage, S3 storage resource has been provisioned and is now backing this. I can connect to it. So this throbbing thing is to draw my attention if I want to learn how to connect to it. So it's very easy to see how to connect to it. So you can just click on this. You install Pinecone, and then you import Pinecone. You get the API key, right? And then you get an index. So here you put in the name of the index. Of course, remember the name of my index is learning rag. This is the name of the index. So the next thing I need to do is to get an API key. So you can go to the API keys here, right? I have a bunch of old API keys here. Probably should delete all of this because yeah, API keys are things, if you're not using them, you should remove them to avoid people hammering your stuff. Anyway, I probably have some things that are running with these API keys. So I'm going to create a new API key and um, learning rag, all permissions. Because we are on a free tier, we don't have the more advanced customized stuff. So I'm going to take this off so that it's not visible. Okay, well, yeah, they actually did a good job of hiding it here. So I didn't need to do that actually. I can just copy the API key and then I'll now go to my code here. I need to put that one. in my .env. So while yeah, so I need to create my .env, and then I can just call it a pinecone API key, and that's the value. Right. Now, um, well, okay, so I think I need to keep a local version of this, but let me just open another window here, api.pinecone.io. Okay, app, sorry, app, not API. API is if I want to do an API call. That's why it was asking me for API key header. All right. Um, I want to get the instructions, but obviously the first thing, I'm not connecting yet, but the first thing you would do is um pip install pinecone. I assume pinecone is already installed, but if not, we'll do that. So I'm going to then copy this piece of code and run it. So we initialize pinecone. Um, you can do this at any point in the sequence, right? Um, right. Now, yeah, so Pinecone is not installed, so I have to pip install it. Okay. The API key, I'll get it. So I have to get the I have to get the .env loaded. So apart from Pinecone, I have to also import OS. I have to import load.env from .env, and then I have to load .env, and that gives me true. Meanwhile, Pinecone has been installed. So it's easy to just connect. API key is os.get and Pinecone API key. And that's it. The index name here, I'll change it to my index name, which is learning rag. Okay. Yeah. So with this, I have connected to the index. The next thing is embed and offset. So this is the first part of it, right? Well, not necessarily in that sequence. If you look at there's a sequence you normally will go through is start by ingestion and all of that. But let's set the things up. So that's setting up Pinecone. Now we set up the um embedding model. So the embedding model, we want to set up the Hugging Face sentence transformer all mini LM. So it's not very difficult. You even also have example here. Um, yeah, you can install this, but sentence transformer is already installed in this particular runtime, in this collab runtime. So I don't need to install it. I can just do this, right? And we can take all of this. So let me just take that and we use it. So we import sentence transformer. Um, yeah, I'm not going to do this yet. Um, so let me import on a separate code block. Right. So then you create a model, sentence transformers, all mini LM, and we have that. And remember, all mini LM has 384 dimension embedding. We can try doing a few things. For example, um, so you can try to see how well the embedding is um, passing a few words, right? Let me just go. get a few sentences. I could just take this example and yeah. So by the way, note that this entire paragraph has a single embedding, which is the interesting thing. I could also split it into sentences, into words, and um, or into smaller sentences, and it will also have each of them also have embedding. Of course, when I am creating this, let me put this also in a separate code block so I don't need to keep rerunning it. This is going to download now the model, and it's a small model. If you look at this, you can see the dimension. Um, Model size is 22.7 million parameters. So typically, the size would not be maybe probably a few hundred megabytes, right? That would be about the size of it. Yeah. Okay. Yeah, if you even check what is getting downloaded, you have the config, sentence birth, you have the safe tensors. Safe tensors is the actual PyTorch exported model parameter. That's this is actually where the parameters are in the safe tensors. You can see it's about 90 or so megabytes. That's the size. Everything else is kind of smaller. You also have the tokenizers. All of these are part of, you have the vocabulary. All these are part of the elements that it uses to be able to create the embeddings. Okay, so we have an embedding model. We can now create the embedding for this sentence and print it, and you're going to see this embedding. That's it, right? So this entire long um, list or sequence of numbers represents the meaning of just one concept, this one sentence. We can then store this embedding. So to store this embedding in a vector database is not very hard. Store the um, embedding in the vector database. So if you check it out, you will use the vector store instance that we created, the Pinecone instance. And the Pinecone instance, we created this index, right? The index. So we are going to do index.offset. This is how easy it is with Pinecone. It's very easy, right? You just use offset and that's it. It's so now when you do offset, you have to specify the vectors. It has to be a list of vectors, not a single vector. Okay. So here, luckily, I have, if you look at this vector is actually a list of vectors. This embedding because what I passed in was a list of words, even though the list contained just one, a list of sentences, right? So it contains just one sentence, but it's a list of sentences. So the embeddings is actually a list of embeddings. And if you can actually write it, embeddings or shape, because embeddings is a NumPy, um, it's a NumPy array. You can see it's a list. That's why it has this first dimension. So one sentence of 384 dimension. So I can just offset that directly. Can just offset that. So what offset does is it will insert this embedding, okay? And if this embedding already exists, or if the embedding already matches, it will replace. That's why it's an offset, okay? And that's it, right? But you also can pass in metadata, right? Um, because the metadata is what will match the vector, right, to something else. If you are just doing offset without passing in metadata, then how do you connect, the data back? So what we typically do is offset, then we add the embeddings as well, right? So you can actually just check their API documentation. They have very good documentation. Yeah. So you can check their documentation. You see how to do offset, how to do search, how to do filtering with metadata, and then you also have a Python reference, which if you want to get more stuff, right? So typically after you have passed in the vector, right? Um, okay, the vectors, okay, has to be structured. Um, I've just seen in their documentation, you will see that when you are offsetting, you have to structure, it has a structure. It's not just a simple, um, it's not just a simple, you can't just pass in the embeddings. If we try this, let's just try this and see what happens, right? Um, takes one positional argument, but two were given. Okay, so this is supposed to be a keyword argument, so I'm supposed to put vectors equals that, right? So it's going to offset this, right? The only thing is that the vector, the embeddings has to be uh, following a particular structure, right? And this is typically how the structure looks like, just to be sure. So let me call this vectors. The vectors has to be an array, right? And then inside that array, there are three key elements that you have to add. The ID, which you will use to identify, right? Maybe you can say chunk one. This is like if you are done chunking. Then the second thing is the values. So these values actually refers to the embeddings. The actual vector embedding 0.1, 0.2, whatever, the numbers in your vector for one of them. Okay. Then this is where the thing matters most. By the way, this vector length has to go up to 384. Like, so this has to match the length of your embedding size that you selected in the Pinecone database. Then the metadata is now a very important aspect of it. Wait, this allows you to add additional information on that particular chunk, right? So you collect metadata, the chunk that represented this. So for example, and this metadata is anything. It's not a fixed schema. You can put whatever you like. So, but it has to be a dictionary like this. So I could put something like content, and then I'll put the actual content, right? Which is um this. Okay. So that means I would take um, you know, content would be something like this. Okay. So this is the only metadata I want to put. I could add others, right? But this is the only metadata I want to put. So metadata is a free form dictionary that allows you to choose whatever structure you want and put the stuff. So the stuff that you put in here have to be related to the vector. So in this case, since I only have one element in my embedding, okay, I will use that one embeddings 0, right? Then this embedding 0 is going to be a numpy array. Remember, if you check the type must match, otherwise you have problems. It's going to tell you that the type is not matching. For example, embedding 0 is the first embedding. Of course, it's a very long thing. But if you check the type of embedding 0, you see that it is an ND array, right? It's a numpy ND array, but Pinecone does not accept numpy ND arrays. The only thing it accepts is in this values thing is a list. Okay, so we have to convert it to a list. If not, we are going to have, it's going to fail. But let me just try that. So I have now created vector, which contains all of that. If I now run this, the error I'll get is that the type is not JSON serializable because it's a NumPy ND array. So the way to do that is to ensure that you convert this to a list. So use to list to convert it to a standard list. And then you can then it's offset it. So you see it's offset. The interesting thing is that now that I've offsetted it, if I go to Pinecone to my thing here, you will see that it updates. You see that that record just reflects here. So you can see even the ID that I gave to it, chunk one, right? And then the sentence transformers model, blah, blah, blah. And the interesting thing, it also gives you a similarity score, which is 1.004. So remember, we're using a cosine similarity. So cosine similarity of one means they're exactly the same. Of course, it's comparing against itself. So, um, so you can actually see stuff. And this is the sentence that I did there. So that's just how you offset. So you can see we've done the first two phases. One is embedding, right, using sentence transformers, and two, we offset that particular information into the vector database using the index offset. Okay, so now that we've done that, the next thing is if I had a large document, right, I want to take that large document and I want to ingest it. I'll first take that large document and I'll split it into chunks. So that's chunking. Now we're going to use a very basic chunking um, algorithm. Let's just say a paragraph-based chunker, right? A paragraph-based chunker. I actually have a little code that I have done before. So I'm just going to get that so that I don't waste too much time. A paragraph-based chunker is like if you're using that kind of chunking, let's get that lorem ipsum again. Even though I would prefer a more useful let me look for material that is maybe Wikipedia material on artificial intelligence. So I'm just going to get this. Let's say this is a document that we want to um, ingest. Okay. This is a really long document. I'm just going to um, do very simple text-based ingestion. So I'm not going to overcomplicate things. I'm going to select and copy. The other way we could do is web-based, but we can do the web-based using LangChain, which we'll do later on. But for now, I'm just going to select copy. Okay. And then I'm going to put this document, I'm going to create a document here that contains the document, a new file that contains the document I want to ingest, document.txt. Okay. And then I'm going to paste this whole thing here. Right. So it's a really long and large document. Um, so it has all of that stuff I just copied. Okay. Right. So we have a document. Now we want to ingest this document. It's a pretty big document. I can load the document, os.file. Let's say I need to import fs. Um, file system. Pathway. Okay. Um, Let me just get the chunking. I have a chunking instead of rewriting it. But if we were to rewrite this, it's going to take a bit of time. So I'm going to do both in parallel. Um, so yeah, let's do it. Dev sentence let's just say sentence chunking with overlap, right? So you have a text, you specify the chunk size and the overlap. Now the simpler way would be to um load, okay, you have a text. Um so you can use a simple while loop, and then we would search for basically search from the current um match equals regex is coming here. So let's import regular expression. So the idea is to um yeah, let's say chunk equals. So let's just say we're using full stop, right? A period and a space. Simple. I don't want to overcomplicate things, right? So you look for the first match of you know, full stop and space, right? That's the end of the sentence. Okay. So when we match that, then we'll pull the piece that um leads up to that, and then we take that piece and we check if the chunk size is above. If it is not, we look for the next piece, right? So that's a simple um, sentence chunking algorithm, right? Okay. So okay, the other approach would be um let's split. Okay. Another approach would be let's split. So let's see the regular expression and expression. Um let's just do a simple regular expression and split instead of trying to do a match. So we split it based on sentence boundary. So a sentence boundary could be basically a dot, a simple one. I could go with this, but this is a very kind of complex regular expression. Um, so this will be difficult to explain, but uh, you have a first non-captured group, um, and you're getting what, um, then anything between what boundaries. No, well, this is going to be a bit difficult for me to explain. So let me use something else that is a regular expression that is not that difficult to explain. Um, so this is non-captured boundary, and um, anything that is um, non-greedy, anything that is a dot, an exclamation mark, or a question mark. Basically, this is a character class. So it's saying search for anything inside this square bracket, right? So anything inside this square bracket, whether it is a full stop, a period, or an exclamation mark, or a question mark, right? Search for any of them. And if it is found, okay, match it. So it's going to match either of that. And then this slash S is saying white white space, right? So that followed by white space plus any number of white spaces. Okay. Then I need to have a bracket here. So what this is going to do is going to match either a full stop or a an exclamation mark or a question mark, right? Followed by white spaces. That is, white space can be either a tab or a space bar or a new line or character return or line feed, anything, right? It matches that. So it is going to split essentially at the ends of sentences. That's what this does. If I take this particular regular expression, let's just try it so that you can understand how this works. What's happening here is I take this regular expression and I split this original sentence. So let's look at the original sentence, which by the way, I should have assigned it to something now. So let me assign it so that it can make sense. Um, I could just call it sentences. So let's just call this sentences. Okay. And you can see in this sentence, there's only one period. So it's really going to split this into just one. Okay, so around this, we encode the sentences. Okay, and we get our embeddings. So it's printing the embeddings. We have multiple embeddings. Um, then we can offset it. The offset is not going to change. If we go back to Pinecone, well, I think it might because I think it might add a second entry. It's actually supposed to check the embedding. If the embedding is the same, it will not add another one. So you can see it doesn't add another one because the embedding is the same. Okay. So now we want to do ingestion, document ingestion. So simple basic splitting. So we'll first write function. Okay. So I wanted to test that sentences. So we'll try sentences 0, which is the first sentence. If you split it, yeah, I did not import. So let me import this regular expression. Then you can see it just splits it um, into um, just splits it into a single line. If I had multiple sentences, let's say I had a paragraph of sentences. So this time I'll still go back to Wikipedia and borrow one paragraph from there. So let me just borrow a paragraph that has a few yeah, this has like 2 paragraphs with a few full stops in between. So I'm going to copy this and I'm going to put this directly into this. Okay. So that's paragraph. Now, we'll still use the same regular expression and split this paragraph. So you see how it looks like when we split it. So you can see paragraph uh, paragraph. Okay. So it splits into I would like to see how many let's see parts. So you can check the length of the parts. I'll be surprised if it was just one. So my regular expression has a problem. If it does that, it's supposed to split because I believe this has uh, full stop. Okay, so this is the problem. The problem is that this particular place where I had a full stop, there is no space after it. But my regular expression assumes there is at least one space. And it is actually a correct assumption because if you have a dot without a space after it, I wouldn't consider it as a regular end of a sentence. So, but because of this reference at the end, which comes from the Wikipedia reference, I actually don't get a space at the end of that dot. We also have here where we have a dot after decision making. I was expecting that one to split at that point. Um, so it did not split, right? So it means there's a flaw. Um, there's a flaw in the regular expression. Let me check. The other thing would be just let's make it simple, right? Don't overcomplicate it. I think I'm overcomplicating it, trying to. Oh yeah, okay. I think I know where I missed. I missed this. This is wrong. There should be this sign here, right? Because that sign means don't capture this group, right? But when you put an equals to, it means something else entirely. Okay, so this is how you split. If I use this now, I should get what I was looking for. Um, okay, so we now have four parts to it. I can then print the four parts, and yeah, so it has split this, and basically that's what chunking is, right? You are just splitting text into multiple parts. So these are the four parts. The first one, the comma, and then um, the second, and then the third part. Interestingly, the fourth part is just an empty thing. So yeah, so um, yeah, that's that does a chunking. So that's just to give you an idea of what this does. I need to correct this. Okay, so we split the sentence we split the original text rather based on what sentence boundaries. The sentence boundary in this case is using a full stop, an exclamation mark, or a question mark followed by a space. So this is just a very simple approach. Then, yeah, that's we could have just gone with that and said those are the chunks, right? But then this sentence is different things. Okay. Some of them may be empty, like this one. This one is empty, so I shouldn't count this. So you have to do a bit of cleanup, right? And that's where you now you the rest of this code is basically to just clean up that because we can assume that all sentences are equal. Okay, uh, um, so I'll explain what this does. Um, current current things. Okay. So now we are going to look through the sentences that have been split. As you can see here, there are four of them. Now, for each of them, you now check current chunk size or current. Okay, first of all, but I already have this code, so let me just sentence equals sentence dot strip. So this strip is going to remove any white space at the ends of the sentence. So that if you are just having a bunch of spaces or whatever, it should not count. So that's the first thing is strip. And then um if there's nothing, right, then you just continue because you don't want to waste your time with an empty sentence, right? Then the next thing is we now check because like I said, you have a chunk length that we specify. So here you can see that we specify chunk size to be 100, basically 100 tokens. Okay, now in this case, let's assume that we are taking the tokens to be one word. Okay. Um, so you need to we'll check if this sentence can be added to the existing chunk. If it can be added to the existing chunk, then we add it. But if it cannot be added to the existing chunk, then we start a new chunk, right? So the fact that I have sentences does not mean that these sentences form a chunk. If the chunk size is 100 tokens and that's 100 words, and this particular sentence is not up to 100 words, it will be 20 words, it's not yet a chunk, right? I need to still take this other one and see if I can add to it. But if in adding this next one to it, the length now exceeds 100, then I will add it. I would rather just let this one go on as separate chunk and then make separate chunk, right? So those are the principles for chunking. Um, so to do that check, right? Let me make a comment just to clarify it. So check that the current chunk, um, the adding is to the current chunk does not overshoot. Okay, chunk size. So that's really what we are doing here. So the current length tells you the length of the current chunk, right? Plus length of sentence. So we're using length of sentence, even though that means chunk size is in characters, not in tokens. Well, we can still live with that. So let's leave it just for simplicity. Um, I don't want to overcomplicate things. So you current length plus the length of sentence, right? Plus one. You check that. The reason why you need plus one is the space. There's something you use to put a space in between, single space character. So if you add all of that and it's still less than the chunk size, then you can then append the current sentence to the current chunk, right? The current chunk is actually still a list, but at the end of the day, you are going to, well, maybe that's one way. Another way is, yeah, there's a way you could, yeah, okay, you could do that. So you just append the sentence. Then if the so here's the thing, right? We can also do this if the current chunk is not empty, right? Um, then you add, but or maybe I should do this if not current chunk. That is, if the current chunk is empty, let me make it very explicit so that we know if the current chunk is empty, like this, as we're just starting, then you start off the current chunk by it's still the same thing anyway. Still the same thing. This is just so that, but if not, you append, right? Because if you had to take an empty trunk and append, it's still the same thing. Yeah, so let's just go with simplicity first. Okay, so if it is smaller than chunk size, then you just append the current sentence to the chunk, and then you can increase the chunk length by adding plus one. But if not, then this means that you have to add current chunk to lists of chunks and start a new chunk. But there is a case here where the whole sentence is even longer than chunk size. But we'll ignore that for now because we're not trying to build production code. This is just an idea. So that means you now append um, this to the list. I don't want to do this join thing. We will join it at the end. So we'll just append the current chunk right? Chunks are append current chunk dot join. So it is now that okay, that's correct. That's correct actually. Yeah, the join is correct. So what this does is that remember the current chunk is a list of sentences, but we don't want to store the list of sentences in the chunks. We want to store the entire chunk. So we will use space to join all the chunks, and you have a single paragraph or a single chunk as like a single letter. So you add that to chunks, and then you start a new chunk with the new sentence, right? And then you reset the current length to the length of the sentence plus one. Okay, so that's just a simple process. So by the time you are out of this loop, right? You could be in a situation where you have a a chunk remaining. So you try to handle that. So if current chunk is not an empty um yeah, if current chunk is not empty, then you also append. Okay? And that's it. So this is a simple sentence based chunking. Took a bit of time. Right. So chunking is a very important aspect. Remember, we talked about the different ways. Last time I did a simple fixed size chunking, but I didn't want to do fixed size chunking here because it will split everything in the middle of the sentence. Now we can try this our chunking algorithm, right? The first thing is we have to load the file. So to load the file, we can just use open command or the specify the file path. So the file path is documents.txt, and we're opening it for read. We just want to read. Okay. And we can specify encoding as well, which UTF-8, even though we probably don't really need to read it. Then we will read it um, into this text variable. So um, we can now, okay, so it says no, okay, it's document, not documents. So all right, so we can check text now. You see that text is the entire stuff that I had copied from Wikipedia. It's a lot of stuff. So we now chunk it. So we just basically run this chunk. Oh, by the way, with overlap, I didn't do the overlap, right? Because if I were to do the overlap, um, when we want to do the next one, we don't use split with overlap. So let me just, overlap is going to be a bit complicated. We have to go backwards and all of that. So let me just, uh, let me just do a simple sentence chunking. So that I don't mislead people into thinking that we did overlap. We didn't do overlap. Now, doing overlap really helps with meaning, like I said, but um, don't have the time to do all of that. Okay, so we have the text. We can now chunk it and say chunks equals simple sentence chunking. We specify the text and we can say chunk size of 100, right? We run this, right? And then let's see how many chunks we have. We can just check the length of chunks. That gives us 1,248. So we've essentially split this entire text. 1,248 characters, by the way. We can check the length of the text also. You can see it has 184,000 characters. And we split into 1,248 chunks. That means that it kind of more or less fits our 100 um, chunk size of 100, even though it um, seems like we may have on that done it or something. But you can just print, let's print the first few chunks. Let's print maybe the first 10 chunks to see what it looks like. Oh, yeah, so there's something I forgot. We now end up with an empty thing here. So we should have, I don't know how we managed to miss that, right? But yeah, the first 10 chunks are there. So we can fine tune this thing a little bit where it is when we are appending the sentence, but we have already stripped sentence out here. So um, for some reason, yeah, for some reason, this uh, I'm just wondering how we managed to get to first. Yeah, so I end up with this. I can fine tune that algorithm a bit more, but what I would say is let's add a little condition here and um, and oh, hold on. Yeah, this is where I think I should do it. I should only add the current chunk if the current chunk um, actually has stuff in it. So I'm going to um, just strip. Yeah. So I'll only do this. That will improve it a little bit. So you can see it's not a very straightforward thing, this chunking thing. So it's better to use the libraries that they already have. Hopefully this removes, you now have 1246. So you can see I've removed that empty pad just by putting in that little piece. Okay, so we have 1,000 chunks. 1,000 chunks corresponds to 1,000 vectors. So we can just do the embeddings for that. And let's just say we do it all at once. So we can do the vectors equals um we'll first of all do the embeddings. We'll see the same Hugging Face model. We can pass in the entire chunks, right, that we have created. Um, we just pass in the entire chunks. Hugging Face model can handle it. These models are designed to handle large volumes of things. So 1,246 is a small thing for it. So we'll get the embeddings from this. And it's going to take a bit of time. Um, but let's look at the dimensions when it's done. Dot shape. So you will see that there are going to be 1,400 or 1,246. Um, yeah, this is the embedding part of it, and you see it's taking a bit of time. So there'll be 1,246 of it, but all of them will have the same shape, the same length of 384. Then we can create the vectors. So vectors equals we'll use list comprehension. And remember, we're going to create ID. This is how we want to store it in Pinecone, like we saw from the Pinecone documentation. So yeah, we can use any number of things for the ID. What I used before, let me see what I used. I just used chunk one as the ID. So I think we can do that similar thing here. Chunk, um, we can use chunk dash um, um, number. Can just say chunk that's A or I. Let me just call it I. So then that's the ID. Then the vectors. Um, the um, the vector that forms the embedding. Let me just take this from here. Values rather, not vector. That's what I was trying to remember. So values, take the values, and so the values will be embeddings I, okay, to list. Then the metadata will just pass the content. So the content will be the matching content, which is sentences I. So the beauty of it is that this matches um, for I, um, um, yeah. We could also have done, yeah, I think we can just do that for I in enumerate or for I in the other way. I think the easier way is I don't need to enumerate in range length of embeddings or sentences. Hold on. Sorry, not sentences. It should be chunks. Should be chunks. Yeah, not sentences. Sentences was the original sentences, but we've now that was a different thing. This is the text that we're chunking. So yeah. So this is the vectors, right? Now we can just look at the vectors again. We can just look at maybe the first four of them that have been generated. Um, okay, it's different from what I was expecting. Um, yeah, okay, it's printing the entire thing. So yeah, it's printing. Okay, yeah. So this is it. So you have metadata content. So you have the ID, you have the values, which is the entire vector embedding that you can see here. Then the metadata. So I think that's actually what we want. And this is what you now offset into Pinecone. So you can take the Pinecone index, offset vectors equals vectors. And that's it. Um, yeah, so I was expecting this kind of challenge. So this is a kind of course, rate limiting from Pinecone because um, well, we're not on a paid thing. So I can just do for simplicity, I'll just do two steps. So the first step, I'll take the first 1,000 since I'm limited to 1,000. Then in the second request, I'll put in the remaining. Um, so it says updated count is 1,000. I'll now put in the remaining. So that'll be from 1,000 to the end. So this one will take in the remaining 200 or so, 246. If you now go to, of course, you see all these new additional vectors that have been added. And you also see all the similarity scores, right? Let's see if this will refresh indexes. Um, Learning, right? Okay, so you can see, uh, you also see you can then do similarity search. So it says record count is 1,247. Remember, I had one record before, and then I added 1,246. And you can see similarity scores are all, the top one is always one because the top one is what is used to compare similarity with these other ones. So this is the first part of the RAG, which is the ingestion. So I've essentially ingested this document. I've split it into chunks and I have put the chunks into the vector database. Now, the second phase is retrieval. So for retrieval, somebody will ask a question, you have a query, then you do an API call. So in this case, let's assume the LLM we want to use for retrieval is a regular, maybe OpenAI based. So we'll import from OpenAI, import OpenAI, right? Um, so we'll now create a new client. Um, and we specify the API key. We'll need to get get, we need to get the products. Let's just use we use open root uh, let me use Gemini. Um, so you can now the difference. Well, so use Google Gemini. Let's use and then base your own is uh, GTP open. Okay, so I have set up the Open Router API key. Same thing as what we have been doing in my .env. I've reloaded a .env and then I will create a new client. So this was failing before because I had not pulled that API key. Um, yeah, let me just confirm that the API key is there. Um, okay, so it's not there. Um, okay, it didn't get saved because of the network issues. Uh, all right. So I think I have that now. Okay. So the client has connected successfully. I can now go ahead to make any um, API call. So now let's put all the things together. So you can see that we have done the retrieval part, we've done the ingestion, we've set up the embedding vector, we've set up the pine cone, we've done the ingestion of the document, we've chunked it, embedded it, and we have saved it in the vector database. Now, the second part of it is a retrieval, right? The retrieval part is where I will take that context and use it. So let me just make a function that does that. Okay. Um, let's just call it retrieve. So this is the prompt. You pass the prompt in as, and then, yeah, that's all. Okay. You don't need more than that. So the first thing you do is to embed the prompt. Okay. So when you embed the prompt, it gives you an idea of um, the meaning, essentially. So I get the meaning behind the prompt. And to embed the prompt, you can just say is prompt is you still use the embedding model, right? Um, so the embedding model is the Hugging Face model. We're still going to encode the prompt. The prompt is a single text. So we can still pass in the single text here. It actually works that way. Now we have an embedding. We now do a similarity search. That's the second part. Okay. So these are the steps, right? Step two is find retrieval. Call it retrieval. Okay. Find the top A matching entries in the vector database. So most vector databases will have some kind of equation, or sorry, some kind of function that does that, right? So you would do something like PC, pinecone, you can retrieve, pinecone retrieve, or you can do similarity search, or you can just do search. Let me go check what pinecone has. Um, I sometimes forget. Well, you have query namespaces. So um, this is not what I am used to using, right? But I guess we could use that. I am used to just doing a search. So um, we'll just do the index. Okay, I think I used the wrong thing. Index dot simu query search. Okay. So yeah. So it doesn't sound. Search searches by text vector. Um right. So let's just go with this simple implementation and we can try this out. Okay. Just to show you how this works. You just do let me take this out and run it separately. Okay, so let's say our prompt is what is the what is okay, who who coined the term artificial intelligence, right? Remember, we are getting our data from artificial intelligence. So we'll have an embedding and then we'll do this search. And then I would like to see what the matches look like. So the matches here tell you the number of entries or the entries that match in terms from a similarity search. Yes, I expect this should be top K, not K. Should be top K. And I am search is for uh keyword search. It's not for vector embedding search. So for vector embedding search, you use the other example here, which is query namespaces. Um, the problem, okay, well, let's just try it. There's a simpler version of this. I think it is just query. I think it's just query. Yeah. So we can embed it to list. Um, embedded is not actually a list. Okay, yeah, it is a list. Um, so we'll put that. Okay, it's a single vector. So then you specify the top K. Top K is how many responses do you want to get back? So query namespaces. Yeah, you still need to have namespaces and metric. I don't have any namespaces, so yeah. So the thing is, in Pinecone they have namespaces which I didn't talk about, which you would have to create. So but here there is one namespace that has been created. So I think we'll just use that namespace. The namespace is default. So we'll specify this default as the namespace and we'll use that. So namespaces will just use default. So the namespaces is nice with Pinecone because it allows you to partition if you want to do multi-tenancy, for example, right? Which is something you want to do a lot if you are using that same database. You want to separate so that different people do not have access to things that they're not supposed to have access to. So that's the benefit of namespaces. But right now they just have the default one that's been created. So if you don't specify a namespace, it goes into the default namespace. I didn't think I needed to specify it, but then this is query namespaces, so that means we'll use namespace to scope it. Okay, so then I need to also specify the metric. The metric is cosine similarity in this case. You can choose any other one. Okay, so it's going to find matches, and then I will run that. So you can see the matches here. I could also check the length. Well, it's top five, so it's going to give you 5 matches. Oh, okay, it's 3 matches, even though the top K was 5, which is interesting. So, because then it's based on their similarity to the meaning. So if you look at this, you will see it gives you the response, it gives you the score, right? And then it gives you the vector that matches. So the chunks that match, right? So chunk 1089, chunk 180, and chunk 1147. Those are the ones that match. But it did not give me the metadata, so I cannot tell what that, what those chunks contain. Okay, I think we also have chunk 167 and chunk 184. So, yeah. So it doesn't give me the metadata. If you want the metadata, you have to specify it in this include metadata. You have to specify that it should include metadata. So to do that, I think it is something like include metadata. Yes, include metadata is true. If you don't specify it as true, it will take it to be false. Okay. So this is a part where you do retrieval. So this is what we call retrieval. The retrieval is now I am finding, so you see the metadata is included and you can see the content. And remember the question was who coined? Actually, this should have been who coined, but now it finds the chunks that match. The study of logic led directly to Alan Turing. So it's kind of taking you to chunks that are close to that question of who coins the name. It's basically going to talk about get chunks that match that part. Um, yeah, so this is a scored vector. The first chunk 1089 contains um, Lighthill James 1973 Artificial Intelligence a General Survey, right? Even though this doesn't contain enough context to know what that is. This other one contains, the content is the study of logic led directly to Alan Turing's theory, blah, 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 blah. This one has a score of 0.652. So you can see, of course, the higher scores are the ones at the top. Contemporary approaches to artificial general intelligence. This one has 0.64550. Elisa Yudkowsky, who coined the term, argues that developing, you can now see that it is actually pulling chunks that are close to the meaning. And then the problem of creating artificial intelligence would substantially be solved. They had, however, um, underestimated the difficulty of problem and all of that. Okay, so we have top 5 retrieval. Um, we've gotten the response. Maybe we should even put this into yeah. So let me put this back into the retrieve function because I took it out of the retrieve function just to show us how it looks like. So I'm going to put it back into the retrieve function. Okay. And basically give you matches. We can just return this. So you now want to, the other thing you can pass in here is top K. So that maybe typically we go with 5. So I can pass in the top K here. Metric is cosine, top K is top K. Okay, so this is now the retrieval part. And then the last part is augment and generate. Okay, augment and generate. So Augmenting, of course, is you now make that as a context. So the augment part is you make a prompt. Maybe you can call it a system prompt. It's not really a system prompt, but you can just say a RAG prompt. So a RAG prompt is typically written in this kind of form. Um, you are a um, knowledgeable, knowledgeable AI that can respond to queries to user questions based on additional information given to you. You now have this user query, right? And then yeah, and then you put the query here. So this is a placeholder, right? User query or user prompt. Um, respond to it, respond to this user query using the below additional contextual information, right? And then you have contextual information. Contextual information. And that's it. So you now have a RAG prompt, right? So that's the augmentation part. So we can now have the generate function, which still uses a prompt, uses a user prompt and just a prompt, that's all. So this will do um, um, call the retrieval, right? So you can say matches. Well, one thing you could do with this retrieval is I'm not going to worry about sending the entire thing. So instead of sending the entire um, bunch of stuff, I just want to send only the matching content. So let's just say retrieved equals this. Then I will take the um, just the content. Okay. I'll just take only the content. Item um, content item, yeah, dot metadata content. Yeah, that's correct. So retrieve the matches. I need to confirm that. Yeah, let's just test this. So retrieve, how are you? Just want to prove that. Yeah. So it is still giving me, okay, I need to rerun this. So the retrieve function is essentially just extracting the content that matches the cosine similarity based on the embedded prompt, right? The top 5 matches. And it will now extract. So it's just the actual content that comes back. That's what the LLM needs. It doesn't need all the other metadata, for example, the which vectors match or the similarity score and all of that. That's not part of generation. That's part of retrieval. So yeah, so I have that. I have RAG prompt. So you can now say matches equals retrieve. You pass in the prompt. You can pass in a top K if you want top K. Um, if you want a different top K, maybe like you want more matches. Like in this case, maybe I could say I want 8. Okay. So this is now all of the chunks that match this question that can give you the answer that is close to that question. Then you take this chunk and you will now use the RAG query. With LangChain, this will be much easier, but we are doing this manually so that you can see the whole thing. We can now take the RAG prompts and we can now make a new prompt. Prompt equals RAG prompt dot we could do format or we could do replace, right? Replace. So let's use replace. So we'll replace the user prompt with a prompt. Okay. Right, it found that, figured that out. So replace user prompt with the original prompt that's passed in. And we can even just chain it, which is what I actually had in mind. Then you replace the contextual image information with the matches that we have found and join it with a new line. So this gives you a new prompt. You now take this new prompt and you can now say response equals client dot so for ChatGPT this should be models dot text. I think it's text generates. There's so many of them I can't remember anymore. um Chat, I think it's models or chat. um um Client dot chat, yeah, okay, dot completions, yes, dot generate, um dot create. I think it is create, yeah, create. um so yeah, and then we'll have messages, and then we specify the messages. So we're only just going to have one human message here. So we'll just make a query. We can, sorry, a list, and then we can say role, or we just put in the message, which is this prompt that we have created. So you can see that this is basically essentially just prompting, and then we return response dot um, um, let's say response of text or content is either text or content. There's so many of them. I can't remember again. Yeah, let's say response or text. Okay, and that's brings together everything, right? We will correct wherever I may have misremembered. So you can see the sequence now. This is the part where we generate. So the generation is made up of three steps. First of all is a retrieval, which is you take the prompt, the same prompt that is given, you look into the vector database, you embed the prompt into its own vector embedding. You use our embedding to do a cosine search, right, against all the chunks that you have in the vector database, and you retrieve the top K that match. And then, of course, since you had stored metadata, which include the content of the chunk, you can then extract the content of the chunk. That gives you what has the basically only the chunks that really are relevant to this particular question. Then you now have a RAG prompt which you have to write that will inject the original user query and then the additional contextual information. And this RAG prompt, by the way, you could have just given the retrieved information back to the user, but it's not going to be very useful to the user, right? That's where the LLM comes in. The LLM comes in by taking that contextual additional information that you have given to it, and then we'll be able to generate an answer based on that. And that is the full thing. So that's the RAG, retrieval augmented generation. So with that, I can now proceed to ask, um, oh, by the way, this, I should remove this. This was used as an example. So let me remove it. We should just take what was passed in. So I can now run this and I can just say generate, and I can put in this one that I had done just to test it. Remember, each time we'll have retrieval. I hope this works. If it doesn't work, then it means expecting either messages and model or messages. Oh yeah, I forgot. We should specify a model as well. I didn't specify the model. I need to specify the model here. So the model, we can use our favorite open router, Nemotron. Um, I don't memorize these things, so I always use a lot of going back and forth to reference stuff. There's too much information these days to memorize. But yeah, it's NVIDIA Nemotron. So I'll keep typing while it is loading. Um, or let me check if I have it somewhere, so it will be faster. Or we could pick any other one, but let's just go with. We could also use GPT 404-0 mini, I think. Let me try that. GPT 440 mini. GPT 4-0 or 4.0 mini. Or maybe just GPT 4.0. I don't know if that will work, but um yeah, that's not a valid ID. Okay, so let's go with a small lightweight Nemotron. Um this is yeah, well, I guess we can go with this one. So let's go with this. Um it used to be possible to copy the um okay, so I cannot copy it from here. So I'll copy it from here. Let's use that one. Okay, 55 billion. Okay. So we have our API keys in place and everything. Um, so messages or zero invalid input, expected object receives string. Okay, so I think we will have to use the full OpenAI. Um, yeah, LangChain allows us to get away with it, but OpenAI doesn't. So we'll have to pass the entire thing, and role is user, and then content is the prompt. Yeah, we can't get away. So, all right, so it's generating. Now, again, this question is how rather than who. That actually changes the meaning. Okay. Um, while that is going on, let me ask for another question. How many AI winters have we had as at today? So what is an AI winter? It will be interesting to see retrieval, what you get, from, by the way, this particular model is very slow. So that's it, right? The process is the same. It's whether you're using Python. I know I didn't have enough time to go to JavaScript, much less LangChain and all the rest. We'll do LangChain next week. But I really just needed to show the entire process, right, end to end for RAG, because RAGs are very important. This is what we call a naive RAG. We've not even done a lot of the things, the problems that we have to deal with things like document ingestion, for example, different other types of documents like PDF, like slides, other different kinds of content. So we've not even talked about that. And we've not even talked about more advanced chunking approaches, right? We're not really going to go into all of that. This is just to give us a grounding on when you hear RAG and what RAG is and how we do RAG, right? What's going on. But at the end of the day, the most important thing that you need to understand is that first, there are two parts to it, the ingestion side of it and the retrieval side of it. In the ingestion side of it, that's where you talk about text loaders, document loaders. That's where you talk about chunking, different chunking strategies. That's where you talk about embeddings, what kind of embedding models you use, what is your embedding size, That's where we talk about vector databases. What's your selection of vector databases? We just use Pinecone now, but there's also Chroma and a bunch of other ones. And metadata, right? Then semantic search, right? Then when it comes to the retrieval side of it, then you have to talk about retrieval. Retrieval seems like, oh, it's already a solved problem, but it is not. Retrieval matters a lot. If you don't retrieve the right elements, the right pieces, you're you're not going to get the right context to send to your okay. So it did all of that and it failed at text. Okay, so yeah, chat completion. Um I can't remember if it is output. Um is it that? Um I need to test this because that took too long. Let's look for a smaller model. This model is too it took too long. So the retrieval end of it, right? Retrieval is key, being able to retrieve the right information that is needed for your LLM to generate. So that retrieval is very important. Even the context window begins to matter. And then, of course, the generation itself, the choice of LLMs and all of that. So those are all the pieces that matter. Are there any questions? Are there any questions? Okay. Um, let's try this again. All right. Since there are no other questions, this is running. I'll share this notebook later on, so that you see how it works. It's actually taking a bit of time. Um, I'll just give a preview while this is running. I'll give you a preview of what you can do with LangChain. LangChain makes this so much easier because what we did here was naive RAG with Python using Pinecone. Now, if we want to do the same thing with LangChain, right? LangChain gives you loaders, gives you splitters, it gives you embeddings. Of course, embedding vector store, it gives you retriever, a concept called retriever and the LLM. And we're going to look at how to do that. You have a lot of loaders. Um, you could actually do loading of PDFs and CSVs and other things like that yourself directly. And for example, you can use PyPDF to just load the PDF. But the LangChain has built a lot of this already, so it makes it very easy. It even has a directory loader, so you can load everything in a directory. We'll talk about it in more detail. Then you have splitters. So you have the most commonly used splitter is a recursive character text splitter. So a splitter allows you to chunk following a structured strategy. We talked about different chunking strategies. You have others like the character text splitter and the token text splitter. And then after that, you can do embeddings. So you can use um, they have integrations with embeddings as well. OpenAI um, with Hugging Face and all the rest, right? Then you can then use a vector store like we have just seen. It also has integrations with all of the vector store, the Chroma, Pinecone, and so on. And it makes it easy, just the same way you can directly put in the words instead of going through all the steps that we did. And then LangChain has something called a retriever. A retriever is basically um, you can invoke a retriever and chain it with everything else. Remember, LangChain is all about chains. So when you make a retriever, then you can, chain it um, to other things like the prompt and so on. And you can get a vector store and turn into a retriever. So it gives that idea, that concept. So retriever is basically encapsulating that retrieve function that we did, where it will be able to generate embeddings, do similarity search, and give you the top matching, items. And yeah, so we have different retrieval strategies. Like I said, there's a similarity search, there's a max marginal relevance, there is also metadata filtering, like, you know, using the metadata to filter it. A lot of the vector databases give you that ability. And there are a lot of different advanced retrieval techniques as well. So when doing a RAG, these are the best practices, right? Ingestion, make sure you clean your document before indexing, remove duplicates, preserve metadata. Chunking, make sure you start with recursive chunking so that you can have structure. Use overlap, 10 to 20% like we saw. Test your chunk sizes experimentally. I did a few experiments. Embeddings, use the more modern embedding models. Always re-embed after you have major changes in your content. Benchmark retrieval performance. Then in retrieval, tune your top key. You can adjust your top key to see what it gives you. Use metadata filtering and um, consider hybrid retrieval. Consider hybrid retrieval. So uh, that we'll talk about some of that. Best practices is document chunking, right? Is very key. Embeddings, convert meaning into vectors, vector databases. This is kind of a summary of everything that we have said. So when we come in next week, we will just do the same thing, but we'll use LangChain and see how much easier. But LangChain provides a lot of the um, the cooling also do that. Um, we also do the naive one with JavaScript as well. So that is all. Yeah, so yeah, this finally worked. It took a bit of time for it to generate. So you can see the LLM, given that context that we gave all of those selections, it now says based on the provided contextual information, text does not explicitly state to point the term. So when LLM says something like that, it does not explicitly state, that means it's a problem in retrieval or maybe in chunking because that information is there, but why wasn't it retrieved, for the LLM to have it? So these are some of the factors that really matter when we are talking about things like retrieval, right? In RAG, retrieval is very important. Like I just showed you on that slide. If you don't give the LLM all the right information, it will tell you things like this, right? The context mentions that the field of AI research was founded at a workshop in Dartmouth in 1956. John McCarthy is referred to as an AI founder and all of that. So it it's able to see all the names that were mentioned, but there is no information there that ties a name to who coined AI, right? But if you go and read that article, you will see that it actually was mentioned. So it could be that our chunking was bad. Of course, remember, we didn't do any overlaps in the chunking. We didn't do any overlaps. So we may have lost information, and so on and so forth. So this is something, this is how you test your RAG and you see how well it does. Now, the second one, how many AI winters have we had as at today? So again, based on provide contextual information, there have been two AI winters as of the time frame covered by these sources. We can go check what those sources are. So the first AI winter following publication of Minsky and Pepper's book Perceptron 1969 and all of that. But at least it is able to get information to say there are two AI winters. I think there were actually three. There was a winter in 19 in the 70s. There was a winter in the 80s. There was a winter in the 90s. Even though you could say the winter in the 90s was kind of an extension of winter in the 80s. So that's it. If there are no further questions, then we can end for today.